Welcome to a challenging technical restoration by an international expert. We are watching the meticulous surveying process to search for lost tech equipment by the lake. The submerged environment and saturated humidity are always the ultimate invisible enemies that destroy all electronic circuit structures. There it is. The expert has recovered a flycam submerged deep under the thick mud by the water's edge. The entire gimbal system and motor pivot joints are completely locked up by the hardened clay mud. First, equipping anti-static rubber gloves is the mandatory initial step to ensure safety during chemical operations. Second, trying to fold and unfold the arm axes shows that the mechanical movement mechanism has been severely corroded by rust. Third, the internal LiPo battery pack is definitely short-circuited, leaking electrolyte, and completely unrecoverable. The surface decontamination process begins with a cleaning solution, combined with mechanical scrubbing from a soft bristled brush. Fourth, the principle is to wear away each layer of wet mud without causing micro scratches on the ABS plastic shell surface. Fifth, this clay layer surrounding the heatsink is the primary agent accelerating copper oxidation on the main circuit board. Sixth, every nook and cranny, heatsink vent, and optical sensor must be thoroughly scrubbed to expose the screw locations. A low-pressure spray nozzle is used to wash away the mud mixture, preparing a clean enough surface for disassembly. Completely removing the damaged battery pack. The contact pins and grounding points are terribly corroded with green salt buildup. The technician is using a micromagnetic screwdriver to break through the rust on the propeller shaft. This operation requires an extremely precise amount of torque so as not to strip the weak metal thread profile. The anchor points securing the protective shell, GPS module, and main flight controller are being carefully dismantled. The lake water pressure definitely breached the rubber gasket, waterproof barrier, and flooded straight into the main logic board. Fourth, the outer shell is off, and we are facing a disaster with mud and plant roots invading even the narrowest cavities. The expert has to use fine-tipped tweezers to peel and separate each piece of debris to protect the fragile ribbon signal cables. The motor folding joint is being removed from the shaft. The internal aluminum alloy layer is tarnished due to electrolytic oxidation. The screwdriver tip continues to work on the retaining clips of the PCB housing, where the mud-covered ESC speed controller circuits are located. The motherboard has been lifted out, revealing a grim outlook with a series of rusted capacitors. Fourth, the technician continues to disassemble the lower belly, where the optical and ultrasonic sensor systems are located. Fifth, technical tweezers are used to carefully separate each strand of signal and power cables caked in mud. Sixth, the hidden screw points on the second landing gear shaft are being dealt with. The mud has penetrated deep into the core. The metal hinge structure is being separated, showing the water's devastation on the folding mechanism. Fourth, pulling the three-phase power lines that feed the motor out of the arm shaft requires absolute patience. Fourth, The outer casing of the brushless motor is stripped away. The stator surface and rotor magnetic core are oxidized. Fifth, the magnetic mud layer clinging tightly to the permanent magnets will completely jam any rotation attempts of the coil. Sixth, the plastic cover housing the radio antenna assembly is being removed from the structural load-bearing arm. The expert arranges the disassembled components one by one in order to ensure logical sequence during reassembly. The magnetic screwdriver approaches the third arm again. The unscrewing process repeats with high concentration. Prying open the ABS plastic clips requires just enough force so as not to break the tiny internal plastic snaps. The third motor emerges in a similarly disastrous state. The copper coils have turned completely black from being soaked in mud. The next focus is the heart of the imaging system, the camera assembly and the ultra-sensitive 3-axis stabilization gimbal. The mechanical stabilization structure has been disabled by the mud. Prying open the protective cover must be done very slowly. Third, a specialized surgical blade is deployed to scrape off the dirt splattered on the rim of the optical lens protective cap. The tiny screws securing the CMOS sensor are being removed. Even a single grain of sand getting inside could ruin the sensor. Technical tweezers pull out each component of the camera module, separating the image processing board and the optical lens assembly. All plastic shell components, after stripping away, the circuits are gathered into a large chemical treatment tray. Specialized cleaning powder is sprinkled evenly, combining with water pressure to create an active cleaning foam solution. A large, stiff-bristled brush knocks out the stubborn mud layers sticking to the aerodynamic structure's surface. Fourth, for the narrow heatsink vents on the main body, a smaller brush is used to reach deep inside. Fifth, the mechanical friction process, combined with decomposing chemicals, is slowly restoring the original appearance of the shell. Sixth, the brush continues to break up all adhering grime on every square millimeter of the mechanical framework. The scrubbing must be strong enough to clean it completely, but must not deform the engineering plastic structure. A more compact, specialized brush is used to clean the ultra-thin signal wire bundles and small components. Rinsing off the chemical foam with a fresh water pressure nozzle, the basic module assemblies have shed their mud coating. The delicate details of the optical gimbal assembly are cleaned using a microfiber brush and this specialized prying tool. Entering the aesthetic restoration phase, applying a coat of paint in a stylish mint green for the main body shell. A tech bronze color is sprayed evenly onto the arm shafts. The light, thin aerosol paint coat helps recreate a perfect surface. This protective layer not only creates a visual highlight, but also prevents UV radiation from degrading the ABS plastic. First, moving on to the ultimate challenge. The central control, circuit system, and the motors have been severely corroded. Second, the high-temperature soldering station is activated. The expert is resoldering the power contacts and adding fresh solder to the power supply board. Third, a multimeter is used to test continuity, check trace resistance, and look for hidden breaks. An SMD hot air rework station is deployed to work on the microprocessor, IC, requiring absolute precision so as not to fry the chip. Fourth, applying a precise hot air stream to melt the solder, restoring the pitted, oxidized contact pins. Fifth, excellent. The green LED signaling the microcontroller clock is lit. The motherboard has officially been brought back from the dead. The serviced brushless motors are packaged and labeled. Everything is inspected before entering assembly. The tray of rusted screws is heat-treated using a gas torch. This process creates a permanent rust-proof black oxide film. The paint has fully cured, and the parts are taken down. A metal tray holds hundreds of parts waiting to be reassembled. Specialized silicone lubricating grease is applied, very meticulously, onto the micro gear system of the mechanical folding axis. The planetary drive gear mechanism is fitted into the retaining clip, restoring smooth torque to the structural arm. The magnetic screwdriver firmly secures the pivot hinge assembly with the heat-treated screws, step by step restoring the flexible folding structure. The second drive gear is set into place, with lubricating grease ensuring friction-free movement. The hinge axis cover is screwed tightly onto the arm, sealing the mechanical system inside. The pivot folding clip mechanism continues to be calibrated. This part bears the greatest twisting force. The expert deftly threads the multi-core signal cable bundle through the hollow shaft of the lifting arm. Every cable must be routed precisely, so it doesn't get pinched or broken when the flycam folds or unfolds its landing gear. The optical positioning module and flow sensor are reinstalled into the compartment under the belly. Fourth, the image processing circuit is pressed firmly into the bracket and protected with a reinforced plastic cover. Moving on to the assembly of the 3-axis stabilization gimbal. The flat ribbon cable is bent according to design specifications. The gimbal motor microcontroller board is secured, and the clamping system keeps the structure stable. The newly revived motherboard is placed into the chassis. The grounding screw points are tightened. This is the nerve center that processes all IMU data and manages power distribution to the motors. The camera assembly is linked to the front nose shell. Tiny screws lock the sensor perfectly in place. The bronze-colored structural arms carrying the motors have their 3-phase wires connected to the ESC solder pads. The logic circuitry is complete. The mint green top shell is snapped into the plastic clips, fitting together perfectly. Step 1. The flycam is flipped upside down, and the screwdriver tightens the load-bearing screws, securing the lower chassis and upper shell into a single unit. The final step is attaching the pairs of aerodynamic propellers. The pitch angle of the blades must match the rotation direction. The masterpiece is complete. Inserting the high-capacity battery pack, the power button is confidently pressed and held. The gimbal automatically initializes its self-calibration cycle, and the system successfully connects to the phone app. Fourth, activating the motors via the touchscreen. The 4 rotors roar and slice through the air, lifting the aircraft up. Fourth, The device soars into the clear blue sky, passing through the grid of power lines, marking its total revival. From a pile of muddy scrap, the Flycam is operating smoothly again, a prime testament to the art of microcircuit restoration.